I'm Stefan. Let me quickly introduce myself. I'm actually a PhD student from Germany at the University of Bochum. And I'm researching in computational neuroscience. And at the work we do our scientific computation, mainly with Python. But sometimes I'd wish to be able to interface it with some Java frameworks, and that's why I came across JyNi, which is, and I was amazed by it, how elegantly it bridges Python and Java, and it was so beautiful. Too bad I couldn't use it because our work is mainly dependent on NumPy and other CPython extensions, but mainly NumPy. Then I found another solution for my actual problem. We wrote the data to files and opened the files. Well, we could have done it by embedding or process communication, but still, I kept wondering why it is so hard to add CPython extension compatibility to JyNi, because Java has some layer and CPython has some layer. Can they not be emulated? So now, since I'm standing on a Java summit, I'm not sure how. Wait. Yeah, okay. I'm not sure how familiar you are actually with JyNi. Who has used JyNi here? Okay, so I can do this rather quickly. Okay, but I think just for completeness, I should state some most important facts about it. It is a Java-based Python interpreter. It is a bit more than an interpreter. It actually compiles Python code to Java bytecode. It has multi-threading support. CPython also has some multi-threading support, but it's not so straightforward. And because CPython has this global interpreter lock. Why do they need it? Mainly because of reference counting based garbage collection. Reference counters are not atomic, and using atomic reference counters usually did not yield a sufficient performance. So why does JyNi not need a global interpreter lock? Because its garbage collection is based on Java garbage collection. This regarding finalizers and how weak references break and resurrection, there are some subtle differences. These usually don't matter much, but if you search for them, you can find them, and you can also write incompatible code. But okay. Well, the big killer feature of JyNi is its Java integration. It is very seamless. You can just call Java methods from Python code, just as if they were Python API. The other way around is a bit more complicated. You have to add type information using interfaces. Yet, I hope in the future it will be possible to auto-generate this to some extent by, Python is adding type information now, and maybe, and some IDEs have some very nice methods to pass the type information from comments, and there are some techniques, so it could be improved a bit. The integration is even that smooth that you can have JyNi classes, or Python classes in that case, extend Java classes. Well, you cannot sneak in multi-extension, multi-inheritance, but you can have one Java class and several Python classes. And the big drawback is that it does not support native CPython extensions. Why do I write CPython style C extensions? Because it is Java, and in Java we could have JyNi C extensions, and these would work. Let me illustrate this. We have CPython, which has its CPython extensions. We have Jython on top of Java, which has JyNi extensions. And now guess what? How JyNi would look like? It is actually a JyNi extension that pretends to look like CPython regarding to a CPython extension. So far, so good. Okay, if the motivation is not yet obvious, let me go through it. Okay, we would vastly improve the number of Python frameworks runnable on Jython. Often enough, it is some tiny subtle dependency which would be added, and yeah, tons of frameworks could be made working. Okay. No, please note that everything that works in Jython would also work in Java. And you can have, with some additional effort, build Java API, Java accessible API on top of it. So you could use Python language bindings in Java. Well, it's not so performant, but it would you could achieve compatibility rather quickly and test things out, and why not? And finally, it would allow programs to have simultaneous dependencies on Python code and Java code. And with Python code, I mean also C extensions, of course. So let's leverage all this synergy between the worlds. So when writing JyNi, my main design goal is it shall magically just work. That is the user experience I want to deliver. And in detail, that means having maximal compatibility. Okay, this is an ambitious goal, but so far I don't see showstoppers. It is challenging, it is not always performant, but I think I'm still ambitious to reach at almost 100% compatibility at one day. Then, of course, it shall not have regressions regarding Jython. So, especially multi-threading support should not be harmed. I don't want to modify native extension code. It should work with the original extensions. I even aim for binary compatibility, so it shall even work with closed source extensions. And finally, I also don't want to have changes on the Jython side, on the Python side. Using native extensions from Jython shall just work as if you would do it from CPython. Okay, then there are some subsequent goals. Performance is, the biggest issue is that it will always be kept by JyNi overhead, but I hope that Project Panama can improve it to some extent. I would be happy about some follow-up discussion here. And finally, I would like to have a global interpreter log-free mode. Currently, JyNi introduces a GIL, which is not applied on Jython side, but it is applied once the thread enters native mode, because native extensions might rely on it. But I believe there are several extensions out there that would not need it, would only need it for reference counting. And I think I can circumvent this reference counting stuff. And if the extension does not need it for its own internal synchronization, then it might work. And through this talk, I will sometimes mention some aspects that extensions may not do in order to be suitable for a GIL-free mode, for a potential GIL-free mode. And in the end, I think there could be something like a whitelist of known extensions, and then it can apply a GIL-free mode. Okay, let me start with a proof of concept and a live demonstration. It is still alpha state, and not so much works, but tkinter is a tiny Python GUI framework that already works, at least for some simple example. So, okay, this is a rather tiny program. It just opens a window with a label, and two buttons. One button prints the value of the label, and yeah, the other button, okay, let's look here. This method and these two method definitions are the backends of the buttons. And this one prints the text label, and this one intentionally performs a Java call, yeah, just to prove that JythN is running. And in order to make it also runnable with CPython, we do the import inside the method, which is not such a nice style, but this way the program can run and the error only occurs when pressing the button. Okay. Okay, here is the program again. Okay, let's at first try it with JythN. Okay, this is JythN call by hand without using the launcher. This way you can just call JythN by Java, and with the argument of this program. And yes, it will fail. We have to wait up the startup time, which is not. Yeah, JyNi increases the startup time a lot. Yeah, okay, it doesn't know what to do with the import. So let's run it with CPython. Okay, this is so now we'll see how it should look like. This button works, but of course CPython doesn't know what to do in this case because it doesn't know the Java API. Okay, finally let's run it with JyNi active. Okay, you might recognize the slight difference. We just put the JyNi jar file onto the Java class path, and that's all. No other changes are necessary. And keep fingers crossed, okay. Yes, and we can print this text here. And now also the timestamp works. Just for curiosity, I converted the program to a Java program, so to see how the Java version would look like on top of JythN. It is not so smooth now. The Clam project will improve this a lot, and for instance, yeah, okay, this is the cheap version. You can just inline Python code. And I do this here to do the import stuff because doing it with actual Java JythN API would be very cumbersome. But okay, and the other aspect is that constructors are not nicely wrapped yet. So you have to do some ugly stuff to do the constructors. And yeah, here I defined the interfaces that back up the objects that are used. That is the TK main object. I only use the main loop method from my program, which starts the main loop. And of the GUI components, I only use pack. But after putting the objects under the interface, where's the call? Somewhere there's a call. This to Java does this. Here, to Java converts the Python object to the Java interface. And then I can just do Java code. And if the main purpose, the main operation of the program would be in calling Java methods, I could do my whole code very, very Java-like. And again, also the other parts will be improved with a Clam project. Okay, finally, let's run the Java program, which is actually a bit simplified. Test TK. Yeah, it has only one button now. Here, but we are using completely from Java native C extension API. Yeah, native CPython extension. Okay, let's continue with the presentation. Okay, just in case it would not have worked, I could have shown you this picture. Okay, I want to, yeah, let's say something about the implementation. I guess hardly any one of you did ever take a look into the CPython interpreter source code. Someone who did? Sort of, oh, okay. Okay, if you look into the CPython interpreter source code, you will notice that everything is about something like something called PyObject. How is this PyObject defined? If you search through the headers, you will find this definition. It is mainly consists of a reference counter and of a type object. And yeah, this type object is itself also a PyObject, and it just copies, it repeats this header, and by repeating this header, you do a C inheritance somehow. So let's look how Jython implements this. In Jython, the PyObject is just a Java class, and the methods are just methods. And in this case, the methods are fields in the type object, and yeah, it has one field that is actually a dictionary containing the methods, and the other things are the type name and other operational stuff. So, okay, how to bridge these things? Yeah. Okay, basically we have objects on Python side and objects on Java side, and we must somehow bridge them. One could make a PyObject. Okay, the one with a star is always the C side. We could make the C objects to be just stubs backed by the Java objects and convert all calls through the JyNi layer. We could also do it the other way around. We could have we could create special CPython Jython PyObject subclass that uses a CPython object as a backend. Finally, we could mirror it. We could have a full featured object on Java side and on JyNi side. In this case, we might run into synchronization issues. So it turns out that I need all three approaches. And the CRUBS Java approach is the easiest one, and I apply it wherever possible, depending on the PyObject type. I have a table of PyObject types which says which approach to use. The main advantage is that if the data of the Z object is changed, this is instantaneously visible on the other way around. If the Java object's data changes, it is instantaneously visible. You have no data synchronization issues, but you must have matching Jython type for the CPython type. And the other problem is that CPython often uses macros to directly access internal data of the object. And extensions also use these macros. If Jython has no corresponding type to the native type, for instance, okay, I'm speaking faster than my presentation goes. Fallback approach, if no Jython type exists. For instance, for PyC function, this is a native PyObject that is introduced by the layer, and it is really needed because it wraps the C functions for Python. And of course, Jython has no equivalent type. So this variant of wrapping is the only direction that works here. And in addition, native CPython extensions or CPython Office API for extensions that allow the extensions to define complete custom types. And of course, Jython could not be aware of these two, so this approach also works there. Okay, finally, we have the problem with the macros. Here's one illustration of such a macro. It gets the long value out of the Py integer object, and it's used very frequently. They are defined in public headers, so just looking at the headers, you will get the impression that it's nice to use them. Reading the manual, you will get the impression that it's not so nice to use them, but in the end, this doesn't matter much because they are just used as a matter of fact. Yeah. Yeah, so mirroring the data allows macros to work. But of course, then I run into synchronization issues, which is not so bad as long as global interpreter log is existent, but with GIL-free mode in mind, it is not so nice. But luckily, these macros mostly exist for immutable types, so I get away with an initial synchronization. Yeah, there are some edge cases, e.g. PyList, where I do some other tricks, but I still manage to have only one source of data and also get away without synchronization in that case. Yeah, I can just quickly sketch how this works. Internally, the Jython PyList implementation uses a Java list, but it stores it only typed by the interface, so I can have a custom list implementation and insert this, and that deals with this. Okay, so far so good again. Let's come to the main issue, which is garbage collection, which has the potential to blow everything up. But okay, why is garbage collection an issue? Okay, in my illustrations, I will usually have this gray line. Above the line is JVM world. Below the line is native world. JVM is above the line because it's the high-level language. Okay, let's say we have a native C object. Just yeah, even independent of this Jython and JyNi case now. Yeah. And let's say we have, okay, how can we access it from Java? We would have a Java peer, and that stores a native handle, and by this way we can access the native object through a JyNi. Now, how to do garbage collection? Okay, this is the backend. You could use a finalizer, but we all know finalizers are evil, and so let's do it the right way. We have a weak reference, we have a reference queue, after a GC run, this is enqueued there, and we pull it. Okay, now we know, we see we don't have the handle anymore, so we notice it must be stored in the weak reference. We have a weak reference subclass, and now we are able to use the pulled weak reference to free our native memory. But wait, we could have, there could be other objects that need this. So we have to do reference counting, and this is in fact an incrementation of reference count. Can we have Java objects, other Java objects pointing to this? Because we do a good design, we let them always use the peer and only have one peer, so this is not an issue. But okay, this would work in this direction so far. Let's consider the other direction. We have a Java object, and remember, JyNi needs both directions. We have a Java object, and we want to access it from C side. Then we have a native peer object, and yeah, somehow we must assure that the garbage collector wouldn't collect our backend, because otherwise we have a problem and would probably segfault or something. Okay, in JyNi there's this concept of the global ref, which keeps the reference Java object alive indefinitely until we explicitly free it. Okay, again, so far so good, but now this Java object could point to another Java object, point to another object, and suddenly we could have the situation from the slide before. And now guess what? This one could hold a reference count of another native object, and we can have a cycle. And this type of reference cycle is absolutely immortal, because the JyNi global ref is never freed, because the destructor that would trigger the explicit release is never called because it is ref incremented. And CPython usually deals with reference cycles by active searching for them in their garbage collector. And this search would ultimately fail here because it cannot trace the Java side. Even if we would provide a mechanism to trace the Java side, which I actually did, but mainly for debugging purposes. Yeah, even if we would allow this, then the complicated reference graph would not allow to trace to treat this situation unless we would do a full reference counting on Java side. So tracing is not enough, we would have to count them. But as I mentioned before, reference counting would imply to have a GIL in Jython, which is obviously a no-opt as it contradicts one of my main design goals. So how else could it be done? How is it actually be done in JyNi now? Okay, let's say we have a native object. Oh no, let's say we have several native objects. And let's say we have an entire reference graph on native side. Okay, in CPython this is kept alive, but there you have some entirely immortal objects, which are usually a list of loaded modules and the type dicts. And yeah, these are immortal and keep the reference graph alive. And what I do now is I explore this reference graph by using the CPython traverse proc mechanism that is used by the CPython garbage collector. And I rebuild this graph on Java side with lightweight objects that only store a handle and yeah, I think it's expensive enough, but so let's keep them as cheap as possible. And note here that I don't copy all objects. I only have to mirror those that can have references to other objects. That are exactly those that CPython would register at its garbage collector. Yeah, these tiny objects on Java side, I call them JyGC heads. And also copy this immortal side into static hard references. And I let have every GC head a ref count for its native counterpart. Yeah, and now we can have Java objects that also have a part in keeping something alive, and it this goes through to native side. We can have Java objects kept alive by native objects indirectly now, which is reflected by their GC head. Okay, so you directly see there are also GC heads that have a bit more than the handle. They must keep alive some objects. And this is now the situation where the native object, where I used the JyNi global ref, JyNi global ref before, now I can use a JyNi weak global reference, and the object can still not vanish, because as long as the native object exists, the JyNi GC head exists, because the reference graphs are equal, and a change down here would have been reflected here. There's this updating this is an issue for itself, but so this is kept alive, but no JyNi global reference is involved. Yes, and now let's say some part of the graph becomes unreachable on native side, and I added code that reports this to Java side, and let's say also there are no Java objects anymore keeping Java side alive. Then the Java garbage collector can collect this part of the graph. This triggers reference decrements, and the counterparts to vanish, and finally also indirectly reachable objects will vanish, and everything is cleared. Mission accomplished, isn't it? Okay, let's quickly go. How much time do I have? Okay, then I assume I have some more minutes. Okay, let's go quickly through the variants. We have, if we have just Py objects, I use just normal JyGC heads. In case we have Py objects on native side that are needed by something on Java side, this is the case where I call, which I call Py cpeer, which is itself a Jython Py object. And in this case, I have Py cpeer extend the JyGC head JGC head is actually an interface, and there are a handful of different implementations, and PyCP is one of them. And yes, this here is a very simple, basic implementation used. But such a C peer could have references to other objects. In this case, I use a bit more complicated version of PyC peer that also stores handles to them, so they are kept alive on Java side, or their GC heads are kept alive on Java side, and this also extends JyNi GC head. And yeah, finally we have the third situation, which where the native object has a Java backend, and then yeah, okay, I already illustrated this in the sketch before. So okay, let's take a look now at the hard case. When how can this break? Okay, we have this reference graph right before it would have been deleted by Java GC. Java GC did not yet run, and now let's say some native extension adds a reference on native side by using a macro. The macro way is something that is not detected or not at once reflected on Java side. I try to keep this a rare case. Yes, sometimes I just re-explore, or I do checksums to to find out whether the graph is still valid. But even how much care you take, there can be the situation where the Java GC runs on an inappropriately reflected reference graph. In this case, it would delete this, although yeah, the native side is still needed. And yeah, to make this still safe, before removing the native side, I check the reference graph for consistency. I can check it for internal consistency, and if there are reference counts that are not explainable within this graph, then something from outside must have changed. And in that case, I do a re-exploration of the graph. I don't have to do a full re-exploration because I know the objects that might cause stuff like this, so I can only, it is sufficient to start exploration and at some certain critical objects. But wait, something missing here. What about this guy? Yeah, and to handle this situation, I have to do resurrection. It was the only solution that was feasible to handle this emergency case, which is a rare case. It's just an emergency case. But still, I don't want to have a crash in this case, and so a resurrection must be done, at least with current GC functionality. A word on resurrection, yes. I want to state here that while it is not recommended, it is a legal operation. And yeah, okay, it can only be done from a finalizer. So some certain JGC heads must have finalizers, but I take care that they are only used where needed, and yeah, only for objects where this backend situation is there. And yeah, final resurrection has some more problems. If we had weak references that pointed to these objects, they break. And in a JythN case, we can restore these references by some magic, which works by, yeah, we can delay the callbacks of the weak references for a while, and in case of GC run, we can wait until the deletion of the object is confirmed, and if a resurrection is detected, I can restore the weak references. Yeah. The other problem is that the resurrected object might hold references to other objects that are also resurrected, and these objects might have finalizers, and these might run, although and free up resources that are still needed. and this is also a problem. And we have special finalizers in Jython at least, and for these finalizers I can prevent them from running in this case. Also because once there's a special mode in the Jython garbage collection module that enables a delayed finalization. That means that the actual finalizers only add some methods, add themselves to a list, and after the last finalizer has done this, the whole list is processed. But yeah, in this case, we can also confirm that the objects were really deleted. And these delayed weak reference processing and this delayed finalization is only activated if JyNi is loaded. So no impact on ordinary Jython operation here. So now while I have the attention of some of the JVM core developers, I have a wish list to make this a bit cleaner. One idea would be GC virtuable objects. I imagine there could be an interface that they implement, and if I implement this interface, the object is able to veto on garbage collection. And yeah, in this case, it would be notified that it would have been deleted now, but it actually isn't deleted. Keep in mind that you can already do something rather similar with finalizers. But in contrast to resurrection by finalizers, subsequently deleted objects would not get their finalizers called, and weak references would not break. This would make life a lot easier, at least for the JyNi use case. Okay, obviously I cannot achieve this by reference queue mechanism because that doesn't allow me to keep the object alive at all. Somewhat alternative approach, which would also be a nice addition, but I think I could also do the things in some other way with this, would be a more precise notification of GC phases. I would like to have a listener that is called before the garbage collector explores the connectivity graph and is even able to change it, make some objects quickly reachable or keep them from deletion. So I could prevent the resurrection situation. And I would like to know when clearing weak references starts and ends, and when finalization process starts and ends. There's an unofficial API for some of this around this Java MX bean, but it turned out that it doesn't work properly. Yeah, the events came too early or too late, and I tested this, and yeah, it didn't work. To some extent, I can. So currently, I'm doing this, yeah, by some dirty tricks. I insert a sentinel and add a weak reference and measure the time when it is collected, and this way I have an idea of the time, and then, yeah, in the end, I just wait for the garbage collector and hope that it is done then. And by measuring this time, it is very likely, and yeah. Okay. Very ideal. This could avoid the whole situation. Oh, okay. No, okay. Wrong order. Okay, there would also be some GC features for native perspective. I would like to have standard methods for. Okay, I believe maybe I reinvented the wheel a bit here with this situation. There are several frameworks that have some more advanced native memory management, like reference counting or something else, I don't know. But I think there should be guidelines or standard mechanisms that explain how one should bridge these with JyNi or maybe with Project Panama. Yeah, and I would like to have an interface that tells the Java garbage collector about native memory usage, so it can take it into account when deciding that it should run. Ideally, maybe one could tell it how much memory would be freed by which Java object. Then it could also take this into account. And the very ideal situation would be that one could allow it to trace native objects. And on top of this, one could avoid this whole situation. This would mean basically, somehow bring this mechanism I currently do for garbage collection, make it a feature of the JVM and that would deal with this. Okay, I know probably some of these features were already proposed sometime. I'm not a core developer and I have no idea how hard they might be to implement. Just want to start a discussion. And if there should be positive feedback on some of this, I would also be willing to draft a GEP or something for it. Okay, then today or yesterday I already asked this stuff about this exporting of symbols. The pain with the JVM is that you cannot control how dynamic libraries are loaded, and you need a special flag that allows native libraries to export their symbols to subsequently loaded native libraries. And this flag is usually not used. So in fact, I have to do a workaround. I have to have a layer that is just loaded, pushes through all the JyNi calls, just to be able to load the actual library I need with another flag, so that this library is able to export its symbols to other libraries. So some more control of the symbol loader, or I also discussed it a bit with Charles. Maybe there can be some additions to this. Okay, this is this workaround. More control on JVM side about this would be helpful. Well, then I would have a dream. And that would be that I could have arbitrary symbols that I can define on Java side, back them by Java methods, and export them to a loaded dynamic library for callbacks. I don't know whether this would be possible. I just wanted to state it as an ideal situation. For instance, one could do things like, implementing some graphical framework and loading, let's say, GIMP plugins or something. I don't know the architecture GIMP uses for its plugins, but I believe it's a typical way for plugins to export symbols for callbacks on dynamic library loading. Okay, then some feature work. I think I almost reached C-type support. Hope to get this done in time for the Jython 2.7.1 release. Then I will have to add support for new style classes. And the big goal is NumPy support, which is rather involved because it has so many dependencies on other native libraries. Windows support is also not yet done. Currently, it's Linux only. Yeah, and finally, after Windows support works, which will mark JyNi 2.7.0, I believe, I will focus on some optimization, try to reduce number of JyNi calls that are needed, and maybe explore the guild-free mode. And one day when Jython 3 would be a bit more on the way, I also consider to write JyNi 3, of course, which would be a nice opportunity to use new FFI features of the JVM. Now, finally, I would, in first place, like to thank the Python Software Foundation for funding my trip to the JVM Language Summit. And in second place, I would like to thank you for your attention. Any questions?
What does the performance look like right now? I mean, I assume it's not great, but how not great is it?
I actually didn't test it much. And I think, yeah, it's only so few things workable that, yeah, the performance tests are not so, yeah, not really doable now. But I think the performance should be quite good if there are not so much calls, but few calls that have heavy workload. Right. For instance, which is ideal for NumPy. Yes. Other questions?
I'll
Yes.
just comment that this is like a tour de force of like GC interaction. It's very impressive work. Just the whole getting the cycles between the different garbage collector languages all figured out.
Yeah.
Nice stuff.
Thanks. Thanks a lot. Yes?
So question and comment. I didn't follow all of the interactions between the GCs, but I was just wondering if one of the issues with finalization is that I believe an object can be finalized at most once. So if there's some interaction that causes us to get into this emergency state where the finalizer emergency case would occur again, then we'll
let me quickly go back to that slide. When this graph is detected, I intentionally don't reuse the old objects on top, but I re-explore and recreate the GC heads so that they are new objects and have new finalizers that can run again.
Okay, so you avoid that case then.
Exactly.
Yeah. So another problem, amongst the many problems with finalization we run into is that it's sort of static, whether an object is finalized or static according to its type, which is too strong a binding because as it moves through its life cycle, sometimes you want to register and unregister it. So
The life cycles of the GC generations, or what? I don't know.
For certain, well, I mean, I'm talking about different use cases, but for other use cases, if a situation occurs, you might want to register it for something like finalization, and then if that case no longer appears, you can unregister it. But the problem is you might not have this problem in your case since you create these on demand, apparently. But one of your suggestions was having an interface that allows you to interact with GC in a more fine-grained fashion. And I recommend not making that be part of the type system. Make that be an API so that you can register and unregister it.
Okay. I'm not sure whether I understood this completely, but maybe we can go into it offline again or something.
But yeah,
Okay, but
thank you.
Interacting with different GCs have different notions of phases. They have different cycle rates at which different phases happen. I've certainly, this old GC will do a full GC cycle every few seconds, maybe even faster. And so things that depend on, finalizer lifetime, your finalizer might be running within clock cycles after the object was made. Your weakref might die almost instantly. There's a lot of funny issues depending on these things that asking for that support out of GC is interesting. You should go back to the list of options you had, because some of them look like doable with some hard work, and some of them look like not doable. And maybe, I guess I see Brian thinking that maybe this is an open-ended discussion.
Well, I want to leave enough time to do the few lightning talks that have been registered so that people can get over to fault line on time. So, just being the hovering, casting a shadow over your talk.
Oh, by the way, what I forgot to mention about GILF remote, what extensions may not do, since extensions can almost do anything they want, they might create islands of such immortal objects. They could have other side variables that are not reachable but still hold reference count. And this would break a potential GILF mode. For this usual mode, it is not such a problem because if they do it properly, they have to register it at the CPython GC, which is in this case re-implemented by me so I can detect it. But I said the second idea first. To have GILF mode, I would have to not only to replicate that graph, that part of the graph that can have references to other objects, I would have to replicate the whole graph, because guild-free mode would mean that reference counting on native side is not trustable. I would monkey patch the deallocator and just completely ignore the reference counting and use this mechanism for all native stuff. And yeah, since in that case, such islands, such unreachable islands, could also consist of objects that are not reported to GC. Yeah, these are situations there. These are things that native extensions may not do to be suitable for guild-free mode. And also this, one moment. This this hard case, this emergency resurrection and everything would also not be possible for guild-free mode. Guild-free mode extensions must not cause this situation. Okay.
If you ignore ref counts, you lose the time of the finalization, and I think a lot of Python people expect rely on it.
No, I think officially there is no guarantee on the timing of the finalizers.
And a lot of people depend on it.
I just repeat the answer I got from the Python mailing list.